Monotonicity, quite the word. It is a corollary to the mean value theorem, meaning it builds off of it. So, to recap, let's go over the mean value theorem. We have a function f of x from a to b, and we assume that it is continuous on the closed interval a to b. By continuous, we mean that it has no jumps. So imagine drawing this curve with a pencil. You can't lift it up. That's what it means by continuous. And by closed interval, we mean with endpoints. Endpoint here and endpoint here. We also assume that it is differentiable on the open interval a to b. By differentiable, we mean that it has no sharp turns. Anywhere on this curve, it is not pointy. It is smooth throughout. And by open interval, we mean without the endpoints. So this interior yellow region. Now, what this theorem states that there exists at least one point C within this open interval such that the derivative at that point is equal to this, or the displacement slope. By displacement, we mean the difference from A to B. So it is the slope of this line. Now right away, we can see how there's several points that equal the slope at C1, at C2, at C3. But this visual alone is not enough to prove the theorem. But the purpose of this video is not to prove this theorem, but to build off it. So we shift our focus to monotonicity. Now, building off the assumptions in the mean value theorem, there's two parts to monotonicity. The first part, if our derivative is greater than 0 in our open interval, then we say that the function is increasing on the closed interval, or it is monotonically increasing, which means that for any subinterval in that, the difference is it's always going up. And similarly, the second part, if the derivative is negative on the open interval, then we say that the function f is going down on the closed interval, or it is monotonically decreasing, meaning for any subintervals within, the difference is going down. So this is our theorem. Let's go ahead and lazy prove it. Let's start for the first case, the increasing. We build a circle with 4 quadrants. Now, if the derivative is always positive, that means the direction of the curve at any point is in the first quadrant. So let's say our curve started in the following direction, the blue arrow, and it ended in this direction, the red arrow, a slightly less positive direction. Then, if our curve is to be differentiable, that means that it cannot have any sharp turns. So, to get from the blue arrow to the red arrow, it will have to transition or turn smoothly like this. If we extend these arrows tail to tip, we can approximate a curve. Now here we see that the arrows are smoothly transitioning in one direction, so one direction. But that doesn't even have to be the case. The turning could be back and forth. It could be like this, then back, then forth, then back, then forth again, which would draw out like this. And further, the start and end directions could be swapped, where the ending arrow is more positive than the beginning arrow. And now we can say that it's transitioning from here to here. Extending out, our curves approximate to this. And again, similarly, the transition doesn't even have to be in one smooth direction. It could be back and forth, so it could draw out like this. In all this, no matter where the arrow is, as long as it is pointing up, we can see that in any interval, if you focus in, the net effect is that the function f is going up in this closed interval. So this proves the first part. Now let's focus on the second part. We can build a similar intuition where we start with our circle. But now, since at any point of the curve, the derivative is negative, it is pointing in a direction in this quadrant, the fourth quadrant. So let's say our start arrow, blue, was in this direction, and our end arrow, red, was in this direction, which is slightly more negative. If our function is differentiable, then it cannot have any sharp turns, so the transition from blue to red has to be smooth like this. Tail to tip, extending this to approximate a curve, we get the following. And similarly, the transition doesn't even have to be in one smooth direction. It could be back and forth. And we can even swap the start and end directions, and we would get the following pattern. Having no smoothness, we would get this. Just as for part 1, in part 2, we see that Doesn't matter where the arrow is, as long as it is pointing downwards or negative, corresponding to a negative derivative. The overall effect that for any subinterval, the net difference is that our function f is going down in our closed interval. And this proves the second part. Now, another way to prove this is actually to work with the mean value theorem directly. So let's work with a smoother curve instead. It exists on an xy plane, and it starts from point A and ends at point B. Now, according to the mean value theorem, the derivative at any point C equals the displacement slope. But the beauty here is that if the function is differentiable and continuous at any point between A to B, then it follows that it is also continuous and differentiable at any subinterval x1 to x2 within that interval. So similarly, we could generate a mean value theorem case for that subinterval. If we rewrite this expression, we shall get this, where the left side is the difference from here to here. Now, since x2 minus x1 is always greater than 0, it is always going up because x2 is greater than x1. But similarly, we're focusing in on the second case here of monotonicity, so our f prime is always going down. But a positive times a negative is always a negative, so our answer is always negative. So what this implies that the difference will always be negative for this subinterval. And it doesn't matter what our subinterval looks like, whether it's back here, whether it's over here, or whether it's extended to the complete interval. This logic follows for any subinterval, so this proves that it is monotonically decreasing everywhere. And you can build a similar intuition for monotonically increasing. And that right there is two ways to prove this.